Hello, everyone. Today we will learn about related rates. So, this is the name we give for the type of problems which, as the name suggests, have related rates. What this means is the rates of change of two quantities are related. So, in a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. The procedure is to find an equation that relates the two quantities and then use the chain rule to differentiate both sides with respect to time. So, at that point, we will look at a few examples in order to clarify this. We will look at three examples for this section. So, our first example is air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of balloon increasing when the diameter is 50 centimeters? So, the way to start with such types of problems is you have to identify what is given or what is known and what is unknown. So, what is given in this question? What is given is the rate of increase of volume of air. So, they already said in the question that the volume increases at a rate of 100 centimeters cubed per second. So, the rate of increase of the volume of air is 100 centimeters cubed per second. Now, what is unknown is they're asking how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So we are looking for the rate of increase. So they are asking for the radius. So the rate of increase of radius when diameter is 50 centimeters. Now, it's good that we identified the known and the unknown. One other thing to do is to write them as rates of increase. So, the rate of increase or the rate of change. As we discussed in earlier sections, the rate of change can be written as a derivative. So, instead of writing the rate of increase of volume of air is 100 centimeters cubed per second, we can actually write that as dv dt. V is volume, and this is with respect to time. Also, the rate of increase of radius, we can write this as dr dt. Again, r is radius, and we are differentiating with respect to time. So, just one thing to point out that in the unknown, we would like to find the rate of increase of the radius when the diameter is 50 centimeters. Another way to say the diameter is 50 centimeters is to say the radius is 25 centimeters because the radius is half of the diameter. Now, how do we proceed with that? As we read in the explanation above, in a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. The procedure is find an equation that relates the two quantities. So we would like to do that. What equation might relate these two quantities? In fact, for the related rates problems, there are a few maybe equations that you might want to know. Some for area, for volume, and at the end of this section, I will give you some of these equations. But in fact, the equation that relates both of them is the equation for volume. So volume, and in this case, we're using the volume of a balloon. So the volume of a sphere is 4 over 3 pi r cubed. Notice how we have V and how we have R. We just related both of these unknowns. Now again, let's go back to the rule up here. Then it says, use the chain rule to differentiate both sides with respect to time. Notice it's with respect to time that we're differentiating. So let's differentiate both sides. On the left-hand side, we get dv dt. On the right-hand side, uh, this the 3, we send the power here, and we get 4 over 3 times 3 pi r squared. The 3 and the 3 cancel out, so this is 4 pi r squared. However, we are not done. Notice that we are differentiating with respect to t. So if we were to differentiate this part with respect to t, notice that there is no t in there. So this is implicit differentiation. So don't forget to multiply this by dr dt. Now we would like to solve for the unknown. Again, let's go back to where we wrote our unknown. Our unknown is dr dt. So let's solve for dr dt. So dr dt is equal to 1 over 4 pi r squared dv dt. So what do we do with this? We want the rate of change. So we want the rate of change, which is dr dt, when r is 25 centimeters. And is there anything else that we know? We have the known. And when dv dt is 100 centimeters cubed per second. And when dv dt is 100 centimeters cubed per second. So let us plug this in our equation. So we get dr dt is equal to 1 over 4 pi. Instead of r, we can write 25 squared. And instead of dv dt, we can write 100. This gives us 1 over 25 pi, which is approximately equal to 0.0127 centimeters per second if you were to plug it on your calculator. So now it's important to write a concluding sentence. So the radius of the balloon is increasing at the rate of 1 over 25 pi, which is approximately equal to 0.0127 centimeters per second, when the diameter is 50 centimeters. And this is how we would have solved this problem. Let us now move to another example. So a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 4 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So now, in order to solve this type of question, if it helps you to draw it, then draw it. For me, it would personally help me to draw it in order to get a better idea of what is happening. So they are saying a ladder 10 feet long rests against a vertical wall. So we have a vertical wall here. Let's write wall. And of course, we have the ground. So we have a ladder and the bottom is sliding away. So it will become possibly slanted like this. And they tell us that the ladder is 10 feet long. So the bottom of the ladder slides away at a rate of 4 feet per second. We want to know how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. So I just wanted to make our picture clearer, just to define a few things. So maybe call this distance here x, and this distance here y. So in other words, x is the distance from the bottom of the ladder, which is here, to the wall, and y is the distance from the top, so here, from the top of the ladder to the ground. So I just defined these few things maybe just to make the picture itself clearer and easier for us to use. So again, as we did in the previous problem, let's identify what is given or known and what is unknown or what we are trying to find. So what is given in this problem? They tell us that the bottom of the ladder slides away from the wall at a rate of 4 feet per second. So, if the bottom is sliding, what variable are we dealing with? So the bottom is sliding, so x is changing, it's increasing. So in this case, we can write this as dx dt is equal to 4 feet per second. Now, the variable that we are looking for, we want to know how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. So I want to know how fast the top of the ladder is sliding down. So we can write this as dy dt, because if the top is sliding down, then the main variable changing is y. So dy dt, we would like to know it's what when the bottom of the ladder is 6 feet from the wall, so when x is equal to 6 feet. Now, how can we find like an equation or something to relate both of these quantities, to relate x and y? Remember that in here we have a right triangle, so we can use the Pythagorean theorem. So x squared plus y squared is equal to 10 squared. So x squared plus y squared is equal to 100. And as we did before, we differentiate both sides with respect to time. So let's start with the x squared. If I were to differentiate it, I get 2x. And don't forget, because we have no t in here, and we are differentiating with respect to time, don't forget to multiply it by dx dt. Same for the y, we get 2y, and we multiply it by dy dt. Now the derivative of 100 is a constant, so the derivative is 0. Now, what do we do at this point? We solve for the unknown. What is the unknown? The unknown is dy dt. So we solve for dy dt. So we can write dy dt, or let's start 2y dy dt is equal to negative 2x dx dt. So dy dt is negative 2x divided by 2y dx dt, which is equal to negative x over y dx dt. So now that we know what dy dt is in terms of uh, x and y, so let us plug in what we know about these variables. We know one thing, we know that we want x to be 6. And again, we have the Pythagorean theorem up here. Let us solve for y. Y squared is 100 minus x squared. So y is positive minus a square root. In this case, it's distance, so it's positive. It's square root of 100 minus x squared, which is equal to square root of 100 minus 6 squared. If you were to plug this in on your calculator, you get 8. So that's something we can use. So now we know x, we know y, we are missing dx dt. What is dx dt? Let's look up where we wrote our given. It's given to us that dx dt is equal to 4 feet per second. So we know that dx dt is 4 feet per second. So let's plug all of this in. So dy dt is negative x, which is 6, divided by 8, which is y, times 4, which is dx dt. This gives an answer of negative 3 feet per second. Notice that the answer is negative. So let's write this down, negative answer, which means the distance from the top of the ladder to the ground is decreasing, because it's negative, is decreasing at a rate of 3 feet per second. Or you can say that the ladder is sliding down at a rate of 3 feet per second. And this is how we solve this problem. Now let us look at a final example. So a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So again, it's really important to have a figure with us. So this is a figure drawn, it's from the book. So just to analyze the figure, they told us that the base radius, so this radius right here, this is 2 meters, and the height of the entire cone is 4 meters. Now we have water inside the cone. Water is pumped at 2 meters cubed per minute. So for the water, it forms a smaller cone inside the cone, which has this height and this smaller radius. So we might want to define a few variables, or you can just define them on the figure, but if you want, we can write that r is the radius of the surface at time t. So again, r is the radius of the surface, so it's the surface of the water. So I'm just explaining what these variables we wrote on the figure are. H is the height of water at time t, which is this one. Finally, a variable which we will be using throughout this problem, I will define it from now. V, it's the volume of water at time t. Note that in all of these, time is in minutes, because that is how it was shown in the above question. So we move on as usual. We find the given or the known and the unknown. So what are we given? It is given that water is pumped at a rate of 2 meters cubed per minute. 2 meters cubed per minute, we have meters cubed. Meters cubed shows that this is volume. Minute is 4 times. So we can say dV dt, so the rate of change of volume, is 2 meters cubed per minute. Now what are we looking for? The rate at which the water level is rising. Water level, the level is this height when the water is 3 meters deep. So we want to know the rate of change of the height, the HDT, it's unknown. We want to know this rate of change when the height is 3 meters. Now, how do we relate these variables? So how do we find the volume of a cone? The formula is V is equal to 1/3 pi r squared h. So this is how we've been relating variables in the previous problems through a formula. Let's look back. We always had a formula to relate them. Again, let's look back. We always had a formula to relate them. However, previously this formula was we only had two unknowns in it. And it's kind of weird in this question right now that V is unknown, R is unknown, and H is unknown. So we cannot work with all of these variables. Since in this problem we are dealing with V and H, let us try to get rid of the R, so we only have two variables. How can we get rid of the R? This is why we have a figure, because figures always help in such cases. So you might notice in this figure that we actually have similar triangles. We have this big triangle and this smaller triangle are similar. What can we do with that is that this side right here divided by 2, so r over 2 is equal to this side here, h, divided by this big side here, so h over 4. R over 2 is equal to h over 4, so we can write r is equal to 2h over 4, which is equal to h over 2. We can use that. We know that r is h over 2, so let's plug that in. So v is 1/3 pi. Instead of r, we write h over 2 squared times h, which is 1/3 pi. H squared over 2 squared, which is 4 times h, which is 1/3. We can multiply the 3 by the 4. So 1 over 12 pi h cubed. Now again, we use the chain rule to differentiate both sides. So on the left, we get dv dt, and on the right, we send the 3 down here, so 3 over 12 pi h squared. Since we don't have a t right here, don't forget to multiply this by dh dt. And 3 over 12, this can simplify to, we divide by 3. So we can simplify this to 1 over 4 pi h squared dh dt. Now, what is our known? What is our unknown? Our unknown is dh dt. This means we would like to solve for dh dt. So dh dt, we solve for it. So this goes to the other side. So this becomes 4 over pi h squared dv dt. Now we would like to plug in what we know, the values that we know, in order to solve for dh dt. So what is h? We would like h to be 3 meters. So I will write this down. H equals to 3 meters. And dv dt, we found it, it was given actually, it's given to be 2 meters cubed per minute. So let's plug these in. So dh dt is equal to 4 over pi. Instead of h squared, we write 3 squared. Instead of dv dt, we write 2. So if you were to plug all of this on your calculator, you will get 8 over 9 pi. So we can write the water is rising at a rate of 8 over 9 pi, which is approximately 0.28 meters per minute. So now I will just tell you a small summary of what we are doing in all of these problems. So step 1, of course, if it helps, draw a figure. Then define some variables if they are not already defined in the question. Then identify your known and unknown. Then use an equation to relate the known and the unknown variables. Just a remark, try to have the relation or the equation with two variables, not more. So in our case, we had three variables. So and this is why we solved for r in terms of h in order for us to plug this in and have two variables, which are v and h in this problem. Then solve for the unknown, then plug in values to get the final answer and write a conclusion with words. Now, here are just a few volumes which might be helpful to know whether it is for questions about related rates or optimization. So feel free to pause the video and note them down.